Light feels simple. You switch it on, and the room fills with brightness. You look around, and everything you see exists because light travels to your eyes. It feels smooth, continuous, like something that spreads out evenly through space, almost like a wave. That's the natural way to think about it. Light moves, reflects, bends, and spreads. When it passes through a small opening, it doesn't stay confined. It expands outward. When two beams overlap, they don't just add together. They create patterns of brightness and darkness like ripples interacting on water. All of this points to one clear idea: light behaves like a wave. And for a long time, that explanation worked perfectly. It explained how light moves, how it interacts, how it creates the patterns we observe. Everything seemed consistent, predictable, and complete, until something didn't fit, because when scientists started looking more closely, when they began testing how light transfers energy, they found something unexpected, not a small inconsistency, a complete break from the wave picture. Light didn't always behave smoothly. It behaved in pieces. Imagine dimming a light source until it becomes extremely weak. If light were purely a wave, its energy should spread out continuously. A faint wave should deliver a small amount of energy everywhere, gradually building up over time. But that's not what happens. Instead, energy arrives in sudden, discrete bursts, tiny packets hitting specific points, one at a time, not spread out, not continuous, concentrated almost like particles. This is where the confusion begins, because waves don't do that. They don't deliver energy in separate chunks. They distribute it smoothly across space. The idea of a wave suddenly acting like a series of individual impacts doesn't make sense within that framework. And yet, that's exactly what experiments showed. Light could behave like a wave when it moved through space, spreading and interfering, but when it interacted with matter, when it transferred energy. Something discrete, something countable, something that arrives in individual units. This forced a radical shift in thinking. Light wasn't just a wave. It had to be something more, something that could act like a wave in one situation and like a particle in another, a kind of dual behavior that didn't fit into any familiar category. Because you expect things to have a clear identity. A solid object behaves like a particle. A ripple behaves like a wave. Those categories feel fundamental, built into the way reality works. But light refuses to stay in one category. It crosses the boundary. It behaves in ways that seem contradictory, switching between descriptions depending on how you interact with it. And that raises a deeper question. If light can behave like a particle, then what does it actually mean to be a particle at all? The contradiction becomes impossible to ignore the moment you look at how light delivers energy. Up until now, thinking of light as a wave made sense. Waves spread out. They carry energy smoothly across space. If you reduce the intensity of a wave, you simply reduce how much energy is delivered. Not how it is delivered, but light doesn't follow that rule. When scientists began experimenting with very weak light, they expected something simple. A faint wave should produce a faint effect. Energy should arrive gradually, building up over time until something noticeable happens. But that's not what they saw. Instead, the energy arrived in sudden bursts, not spread out, not continuous. Imagine lowering the brightness of a light source until it is almost off. You might expect the effect to fade smoothly, becoming weaker and weaker everywhere. But at very low levels, something strange happens. You don't get a uniform dim glow. You get individual hits, tiny flashes of energy appearing at specific points, one at a time. Each impact is localized, as if something small and concentrated is arriving, delivering all its energy in a single event. This is not wave-like behavior. It's something else entirely. To explain this, scientists were forced to introduce a new idea. That light is made of individual packets of energy. Each packet carries a fixed amount, and that amount depends on the light itself, not on how intense it is. These packets are called photons, and once you accept their existence, everything changes, because now intensity doesn't mean what you thought it meant. Increasing the brightness of light doesn't increase the energy of each packet. It increases the number of packets. More photons, not stronger ones. This is a subtle but powerful shift. It means light is not something that can be divided infinitely into smaller and smaller amounts. There is a minimum unit, a smallest piece of energy that cannot be broken down further. And when light interacts with matter, it does so one packet at a time. No partial transfers, no gradual accumulation. Each interaction is all or nothing. This becomes especially clear in experiments where light knocks electrons out of materials. If light were a wave, then increasing its intensity should eventually free electrons, no matter how low its frequency is. The energy would build up over time, but that's not what happens. Below a certain threshold, nothing happens at all, no matter how intense the light becomes. And above that threshold, electrons are released instantly, even if the light is extremely weak. That only makes sense if energy is arriving in fixed units. Each photon either has enough energy to cause the effect, or it doesn't. There is no end. This is the moment light stops behaving like a smooth wave and starts behaving like something discrete, something particle. And once you see this, the old picture collapses. Because now light is no longer just spreading energy across space. It is delivering it in precise, individual chunks, which leads to a deeper problem. If light is made of particles, then how can those particles still behave like waves? The weird effect, one particle, many paths at this point. Light seems to behave like a particle. It arrives in packets. It delivers energy in discrete bursts. It interacts with matter one unit at a time. That picture feels clear, almost comfortable again, until you test it more carefully. Because the moment you try to track what a single photon actually does, everything breaks again. Imagine sending light toward a barrier with two narrow openings. But this time, you make the light so weak that only one photon is emitted at a time, not a stream, not a wave, just a single particle moving forward. If light were truly a particle, the result should be simple. Each photon should go through one opening or the other and land on the screen behind it. Over time, you should see two clusters forming, one behind each slit. That's what particles do. They follow definite paths. But that's not what happens. Instead, something deeply strange appears. Even when photons are sent one at a time, the final pattern on the screen is not two clusters. It's an interference pattern, the same pattern you would expect from waves overlapping and combining. Bright and dark bands, regions where something adds together, and regions where something cancels out. But how can a single particle create an interference pattern? There is nothing else to interfere with. No second photon, no continuous wave, just one particle at a time. And yet, the pattern builds up as if each photon somehow explores multiple paths simultaneously. As if it doesn't choose one opening or the other, but instead behaves like it goes through both. This is where the idea becomes almost impossible to visualize. Because a particle is supposed to have a definite position and path. It should be somewhere specific, moving in a clear direction. But here, that idea fails. The photon does not behave like a tiny object traveling along a single trajectory. It behaves like a spread out possibility, a range of paths all existing at once, interfering with each other before a final outcome appears. And then, when it reaches the screen, it lands in one specific spot, always one, never spread out, never divided. The result is both things at once. A pattern that requires wave-like behavior, built from individual particle like events. This is the weird effect. A single photon behaves as if it takes many paths, interferes with itself, and then suddenly resolves into one location, not gradually, not partially, completely. And this forces you into a difficult position, because you can no longer think of the photon as a simple particle, but you also can't think of it as just a wave, because it arrives as a single localized event. It is both descriptions at once, and neither description is complete. This is the moment where intuition fails completely, because there is no everyday analogy that matches this behavior. Nothing in your experience prepares you for something that behaves like a cloud of possibilities, and then suddenly becomes a single point. And naturally, this leads to the next question. If a photon can take many paths at once, then what decides which path becomes real? The turning point observation forces a choice. Up to this point, the behavior of light already feels impossible to reconcile. A single photon behaves like a spread of possibilities, taking multiple paths at once. It creates interference patterns as if it were a wave. And yet, when it reaches the screen, it appears as a single localized event, like a particle. So the natural question is simple. What determines the outcome? Why does the photon stop behaving like many possibilities and become one definite result? The answer is where everything changes. Not in the casual sense of just looking, but in the precise sense of measuring, interacting with the system in a way that reveals information. To see this, imagine modifying the experiment. You place a detector at the openings, something that can tell you which path the photon takes. It doesn't need to be complex, just a device capable of recording whether the photon passes through the left slit or the right one. Now you run the experiment again. Samey setup, samey photons, samey conditions. But this time, the result changes completely. The interference pattern disappears. Instead of bright and dark bands, you get two clusters, exactly what you would expect if the photons were behaving like ordinary particles, choosing one path or the other. The wave-like behavior is gone. And the only difference is that you tried to measure the path. This is the turning point, because it shows that the photon doesn't have a single fixed behavior independent of observation. It behaves like a wave when you don't measure its path, and like a particle when you do. It's not switching randomly. It's responding to the experimental setup. This was something emphasized by Richard Feynman, who pointed out that the act of measurement is not passive. It doesn't just reveal what's already there. It plays a role in determining what can be observed. And that forces a deeper realization. Before measurement, the photon does not follow a single definite path. It exists in a range of possibilities, multiple paths at once. But when you measure it, you force the system to produce a definite answer, left or right, one outcome, not both. This process is often described as a collapse of possibilities into a single result. Not because something physically snaps into place in a visible way, but because the system is no longer allowed to remain in multiple states at once information has been extracted. And the key point is this. You cannot measure something without affecting it. To detect which path the photon takes, you must interact with it. It destroys the delicate conditions that allowed the photon to behave like a spread of possibilities. So the wave-like behavior disappears, and a particle-like outcome remains. This is why observation forces a choice, not because your mind decides the outcome, but because interaction changes what is possible. And this leaves you with a deeper question. If becoming a particle depends on observation, then what is a particle, really? By now, the idea of light as a simple particle has completely fallen apart. At first, it seemed clear. Light arrives in packets. It delivers energy in discrete bursts. It hits specific locations. That sounds exactly like what a particle should do. But then everything changed. A single photon can behave like it takes multiple paths at once. It creates interference patterns that only make sense if something is spreading out like a wave. And the moment you try to measure it, that behavior disappears, replaced by a single definite outcome. So what is it? A wave, a particle both. The uncomfortable answer is this: it's neither, at least not in the way you think. Particle is not a fundamental thing. It's a description, a model that works in certain situations, especially when you measure outcomes that are localized and discrete. When a photon hits a detector, it looks like a particle because the result is concentrated in one place. But that doesn't mean it was a particle all along. It means your measurement forced it into a particle, like outcome. The same is true for waves. When light spreads out and interferes, it behaves like a wave. But that doesn't mean it is literally a wave in the classical sense. It's another model, another way of describing certain behaviors. Both models work, but neither is complete. And that's the key shift, because it means you've been asking the wrong question. Instead of asking what light is, physics focuses on what light does, how it behaves under different conditions, how it interacts, how it produces measurable results. And those behaviors don't fit into a single category. They require multiple descriptions. This is what makes the idea so difficult to accept. Because your intuition demands a clear identity, you expect things to be one thing or another, a particle or a wave, a solid object or a spread out ripple, but light refuses to fit into those categories. It behaves in ways that go beyond them. And that suggests something deeper, that reality itself may not be built from the simple concepts you use to understand it. Particle and wave are tools, useful, powerful, but limited. They help you predict outcomes, but they don't fully capture what is happening underneath. The deeper structure is something else, something that only reveals different aspects depending on how you interact with it. And once you accept that, the paradox begins to dissolve. Light is not switching between being a wave and a particle. It is something more fundamental that can appear as either, depending on the situation. And that realization changes how you think about reality, because it means the world is not made of simple, well-defined objects behaving in predictable ways. It is made of interactions, of possibilities becoming outcomes, of systems that don't have a single fixed identity until they are measured. And light, something so familiar, so ordinary, is your first glimpse into that deeper truth. Not that it's strange, but that your expectations were too simple to understand it.